Greetings and welcome to the recitation video for problem set number 3 of Chemistry 221, where we'll look at chapter 3 in detail. And like the other ones before on this problem set, try the problem set first on your own. Make sure you show your work. Don't just give me the answers. Make sure you use a periodic table. Again, I recommend mhchem.org/per-tabs periodic table. That'll be the one you'll use on quizzes and exams, stuff like that. You don't have to watch this video from start to end. You can scrub through it. You can put me at 1.25 speed or whatever. Any of these ways are fine. It's really important to me that you mark every problem. Mark the ones that you got right with some kind of self-correct mark. Also the ones you miss, which is totally fine, by the way. Just make sure you put at least the right answer, maybe some notes how to do them better next time, and that's great. You turn in a problem set which is perfect, but no self-correct marks, you will not get full credit. On the other hand, you can miss like every problem, but if you self-correct, no worries, full credit. So it's really important to me that you mark your problem. You can talk to me, you can talk to the Avid LSC Center if you have any questions on this material. It's no problem at all. Without further ado, let's see what problem set number 3 has to offer. So let's get into the problem set. So question number 1, it says, consider the electromagnetic spectrum and what color of light has photons of greater energy, yellow or blue? And it also says which color of light has the greater frequency, blue or green? So to answer this question, you need to look at the visible portion of the electromagnetic spectrum. And there's a list in the lecture notes or on the or in chapter 6 of the textbook. And when you have this list, you have to realize how energy and frequency work. And there is a way to talk about the energies per photon. A photon, of course, being the smallest piece of light. Here's the thing we used in the lecture. In the lower right is what I'd kind of like you to focus on. That's the visible spectrum, all right? It's a very narrow part of this whole thing, the whole picture, and that whole thing is the electromagnetic spectrum. So when we talk about the EM spectrum, all right, it goes really from gamma rays on the left to radio waves on the right. Visible light is just a very narrow region in the middle, and you can see the other types of EM, X-rays, ultraviolet, infrared, microwaves, etc., etc. Now, the visible light part on the bottom, the values for the colors, all right, blue on the left and red on the right, are listed by wavelength. Wavelength is literally a distance between the beginning of the wave and where the wave like starts again, if you will. And those numbers starting at 380 nanometers and going over to 780 nanometers, those are the wavelengths of visible light. And remember, a nanometer is 10 to the minus 9 meters, so very, very, very small wavelengths. There are relationships between the energy of the electromagnetic spectrum. This thing right here, which kind of looks like an upside down Y, is a Greek symbol for lambda. That's the wavelength. And wavelength is also related to the frequency. And then along the way, we saw how C, the speed of light, all right, is a constant that's going to be important, and also H, Planck's constant, is going to be important. But for this problem, we don't really need any of these kind of things. You can see here on the kind of middle part of this picture, there is a frequency graph. And you can see it goes from 10 to the 20th there by gamma rays down to 10 to the 8th radio waves, all right? And the visible light is kind of in the middle. So you can see there how if this is a proportional scale, and it is, blue is closer to the gamma ray side, so that would have a higher frequency. 780 nanometers, on the other hand, would be closer to the radio wave side. That would have a smaller frequency. So you can see here that the wavelength numbers are getting bigger as you go left to right. On the other hand, the frequencies, all right, remember blue is closer to gamma, red's closer to radio. The frequencies are decreasing as you go left and right. So what that means for us here is that frequency and wavelength are inversely proportional. One goes up, the other one goes down, stuff like that. And finally, using the expression E equals h nu, you can see that frequency and energy are both proportional to each other. So what that means is as frequency that would go up, the energy would go up, and as the frequency goes down, the energy goes down. So we saw here that the blue light with the smallest wavelength should have the largest frequency, and largest frequency by default means largest energy. So in both A and B, you can see blue is one of the colors. Blue would have highest frequency and therefore also the highest energy. So for example, on A, yellow is more towards the red side. Yellow would have a bigger wavelength, it's true, than blue, like 600-ish nanometers would be bigger than 380 nanometers for blue. On the other hand, bigger wavelength means smaller frequency and smaller energy. So for all of these reasons, we would say blue is the answer for both A and B. Blue has a higher frequency, it has a higher energy than most of the other colors on the periodic table. And definitely when compared to yellow and green, that would be the case. Yellow and green are more kind of in the middle. But the important part for us here is that energy equals h nu equals hc over lambda. So what that means is that the frequency and energy directly proportional. One of those goes up, the other one goes up. But because wavelength is in the denominator, as energy or frequency go up, the wavelength is going to go down. Wavelength is inversely proportional to energy. Now, in 1C, we have a whole bunch of different types of electromagnetic radiation. It says put them in order of increasing energy. So remember on that last slide, which I believe I'll show you here in a second, it shows frequency increasing, and as frequency increases, the energy will increase. So what we have here is we have radar, which is basically a radio, which is one of the types of EM radiation. Radar is an acronym for radio detection and recognition. Next time you play Jeopardy, you'll be good to go on that one. But anyway, radar is radio. The next one, it says radiation, but it's microwave. All right, radiation is basically an energy emission from a type of EM. This is quote-unquote microwave radiation. But the important part for us here is not the radiation, it's the microwave. So we're comparing radio in the first one to microwave in the next one. Gamma rays are the third one. Red light means visible light. And finally, ultraviolet is the last one, and it says put these in increasing energy. So on that picture we just saw, we want to put them basically from lowest frequency to highest frequency, because remember, frequency and energy are proportional to each other. So knowing that, you can see that radio, which is radar, is on the far right. That's the lowest energy. Then we'd have microwave, then we'd have visible, ultraviolet, and gamma rays. So the order then would be radar, because radar is radio. That's the lowest energy, lowest frequency. Then microwaves after that. Visible kind of takes a spot in between there. Ultraviolet, gamma rays, good to go. The little symbol there is a gamma, just as a quick reminder. This little thing right there, it looks like a weird Y, I guess. That's the Greek symbol for gamma. If you see it, you'll know what we're talking about. The most prominent line in the spectrum of magnesium, 285.2 nanometers, but there are other lines at 383.8 and 518.4. In what regions of the EM spectrum are these lines found? What is the most energetic line? What's the frequency and energy in both joules per photon and kilojoules per mole of the wavelength of the most energetic line? Okay. So the first part of this question, let's figure out what region these lines are found out and also which one is the most energetic. And from the most energetic line, we're going to do calculations on it. We're going to find the frequency, energy. Now, these are all nanometers, so these are all wavelengths, all right? And on question number 1, we saw that wavelengths, as they get bigger, the energy decreases. They're inversely proportional. So if we want the biggest energy, we want the smallest wavelength. So let's make a prediction that 285.2 nanometers is the highest energy. Now, on the other hand, it does say what region are they in. If you look back in that table, 285 and stuff is more likely an ultraviolet. 383 and 518 are arguably visible. 383 is right on the edge of ultraviolet and visible, so if you said ultraviolet, it's not a big deal. Visible light is roughly 380 to 780, so that's why I would think the 383 and the 518 probably visible. All right, but on the other hand, 285 is definitely not. That one's going to be ultraviolet. So for this answer, I would say 383.8 and 518.4 probably visible. 285.2, which is just to the left if you're looking at the last slide, ultraviolet. And again, smallest wavelength, highest energy, 285.2 nanometers would be the most energetic. And again, if you put down ultraviolet for 383.8, not a big deal. That's kind of a rough guide there to wavelengths. It's not exactly perfect. Now that we know that 285.2 nanometers is the most energetic, we can now calculate in the next slide frequency, energy, etc., etc. Using the 285.2 nanometer value, which was the highest energy wavelength in the last part of question number 2, we can use that now to find the frequency. We can also use that value to find the energy in both joules per photon and kilojoules per mole. So speed of light, c, a number I want you to know / memorize, equals wavelength times frequency. And so that's how we're going to solve for the frequency. Frequency is going to be speed of light divided by wavelength. Now, speed of light is usually recorded in meters per second, so we're going to have to turn the nanometers into meters first. There are 10 to the minus 9 meters per nanometer, so that comes out to be 2.852 times 10 to the minus 7th meters, pretty small. And then on the next part, you can see frequency equals speed of light divided by wavelength. Speed of light, 2.998 times 10 to the 8th meters per second divided by the wavelength in meters, you get 1.051 times 10 to the 15th inverse seconds. Remember, if you see seconds minus 1, that's just another way of writing 1 over second. And if you don't like any of those, you can also write hertz, HZ, which is fantastic. The speed of light says meters seconds minus 1. That's just another way to say meters per second, so don't let that intimidate you. But anyway, that 10 to the 15th number, that is the frequency. Now, to find the energy in joules per photon, there are two ways you can do it. You could take Planck's constant h and multiply it by the frequency we just calculated, and that would be an excellent way to do this. You can also find the energy per photon by E equals hc over lambda. Then you use Planck's constant and the speed of light. You would divide by the wavelength in meters once again, use the established way. Either way is okay. So in this example, I went Planck's constant, 6.626 is all you have to know, times 10 to the minus 34, times the speed of light, 2.998 is all you have to know, times 10 to the 8th, divided by the wavelength in meters, 6.965 times 10 to the minus 19th joules per photon. And again, you could have also calculated this number by taking the frequency, 1.051 times 10 to the 15th, multiplying it by Planck's constant, 6.626 times 10 to the minus 34. Good to go. This is the joules per photon, the smallest piece of light. And you can see it's not a very large number. There's not a lot of energy per photon. So to turn joules per photon into kilojoules per mole, all right, you can take that joules and turn it into kilojoules. There's 1,000 joules per kilojoule. So you could divide by 1,000 or multiply by 10 to the minus 3, either way. And then you can also use Avogadro's number, 6.022 times 10 to the 23rd. You would multiply Avogadro's by the joules per photon to get the answer. So when I did this, you can see that in this problem, I basically just recreated this part right here. And then on the end right here, here's the Avogadro's number. We're going to multiply it. We're going to either divide by 1,000 or multiply by 10 to the minus 3 kilojoules per joule. Either way is fine. 419.4 kilojoules per mole is the energy. And this is kind of cool because that magnesium line at 285.2 nanometers actually gives off 419.4 kilojoules per mole. If you happen to have a bond transformation that requires that much energy, in theory, all you'd have to do was just shine a light on it for a while, and then that'll make the bond break. It'll form whatever you're looking for, and you're good to go. So this is an example of how photochemistry can be used. You can figure out the transition of a light beam and then see how it applies to a chemical system to enact chemical change. Question number 3. Considering only transitions from n equals 1 through n equals 4 for the hydrogen atom, A, how many emission lines are possible, and B, what is the lowest energy transition is basically what B is saying, and on C, it's saying what is the shortest wavelength. Okay, this question is basically about the Bohr model for the atom, and in the Bohr model for the atom, which worked really well even to this day for hydrogen, but not so well for multi-electron systems, there were a series of levels, and this little picture kind of shows what we're talking about here. In the Bohr model, all right, the nucleus is right there, and the first level is n equals 1. So n equals 1 is closest to the nucleus. And electrons, for whatever reason, a lot of times wish to leave home, all right, which means in this context, they're leaving the lowest energy level possible, which is n equals 1. Chemists call this the ground state. They leave the lower ones and they go to a higher level. So for example, my cheesy arrow there shows a transition from n equals 1 to n equals 4. Now to remove an electron from a lower orbit to put it in a higher orbit, it takes energy. It's an endothermic process. Those are called absorption lines. And absorption lines are really cool. They're very helpful if you watch forensic shows. A lot of times they use absorbance spectroscopy to see what's happening, what kind of samples are around and stuff like that. But for right now, what we're focusing on more are the opposite lines. So let me get rid of that little thing I just wrote, and I want to talk about what is an emission line. And emission lines reflect the fact that the electron has gotten to a higher energy level and it basically wishes to go down to a lower energy level. So an emission line is when you have a transition from a higher level to a lower level, from a higher N to a lower N. And these kind of transitions are exothermic. So if the transition corresponds to a wavelength that our eyes can see, you can actually see it. Okay. A practical application of this is a light bulb. If you're using a light bulb right now to see all of this stuff, light bulbs are essentially emission creators. They create energy by electrons being excited to a higher state, usually through electricity. And then as they come back down, they release energy, light and stuff, which you can use to see. Woohoo! So anyway, this question A then says, how many emission lines? It's basically saying how many higher level N to lower level N lines are possible in the first 4 transitions. And you can see there that my cheesy 4 to 1 transition is actually one of the possible transitions. The electron could have also, though, went to 4 to 2, or it could have went to 4 to 3. So all 3 of those little cheesy lines right there are transitions. Those are 3 of the emission lines possible. But really, there's no reason why the electron had to start at n equals 4. Maybe it only made it up to n equals 3. All right, cool, no problem. So you could have a 3 to 2 transition, and you could have a 3 to 1 transition. So again, cheesy arrows. Sorry, I can't draw on this thing worth anything, but hopefully you get the idea. 3 transitions from n equals 4, 2 transitions from n equals 3. And there's, of course, also one possible from n equals 2 to n equals 1. So on this problem, there's a total of 6 different emission lines. And again, because these are exothermic reactions, exothermic processes, higher n to lower n is what you want. So the 6 emission lines, instead of my cheesy arrow drawings, which look like a kindergartner made them. Anyway, I can't draw. It's a long story. Anyway, 6 emission lines possible. You can write them 4 arrow 3 as a 4 to 3 transition, 4 to 2, 4 to 1, 3 to 2 and 3 to 1, and 2 to 1. Now, the next part is kind of cool. Remember, science is all about chemistry, and physics anyway are always about the energy. And energy is literally the y-axis. So on B, it says it's looking for the lowest energy. It's looking for the smallest arrow. Now, these arrows, these levels, shells, okay, they're all related by a 1/n² dependence. And without getting a lot into detail, hopefully you can see that the gap from 1 to 2 is bigger than 2 to 3, but 2 to 3 is bigger than 3 to 4, and 4 to 5 would be smaller yet, and 5 to 6 even smaller, blah, blah, blah. So the smallest arrow that we drew up there just now was the 4 to 3 transition, all right? The 4 to 3 is the smallest gap. So when it says for on B, photons of the lowest energy, that would be the 4 to 3 level. The 4 to 1 would be the largest level. And then the last one says which one has the shortest wavelength, okay? Well, like we've seen already in this problem set, E equals h nu, which equals hc over lambda. And that lambda, that upside down y, that's the wavelength. And wavelength and energy, you can see like one is on the top part and one is on the bottom. So what that means is that for us, smallest or shortest wavelength is going to be the largest energy. So we also, the answer for C is not going to be just shortest wavelength, it's also going to be largest energy, and the largest arrow is definitely the 4 to 1 transition. So the 4 to 1 transition has the highest energy, and because energy and wavelength are inversely proportional, that would also be the shortest wavelength. A beam of electrons with a mass there of 9.11 times 10 to the minus 31 kilograms per electron has an average speed of 1.3 times 10 to the 8th meters per second. So that's a pretty good clip. Anyway, what's the wavelength of electrons having this average speed? And it says no physics fans, no relativity. Okay, this is a question where wavelength is associated with it, but it's different than the previous wavelengths we've seen. This one here is the wavelength of a particle. A particle is something with some mass, and here you can see that the electron does have mass. The photons and electromagnetic radiation we talked about earlier, they don't have mass, okay? So if you have something with mass, with grams, kilograms, pounds, although try not to use them in my presence, but you get the idea, this is when you have to use a different equation, and this is what they call the de Broglie wave equation. And the de Broglie wave equation also has a wavelength in it, but it's a different kind of a wavelength. It's the wavelength of a particle. And again, this blew scientists' minds because particles shouldn't have waves and waves shouldn't have particles, but they saw both, all right, which is totally crazy. The photoelectric effect was when light, photons without mass, was acting like a particle. It was pushing the electrons out. So this area gets really trippy compared to the world that we're used to. The de Broglie wave equation is lambda equals h over mv, this part right here. And in this equation, you must use kilograms, okay? A joule, which is what Planck's constant has, a joule is really equal to a kilogram meter squared per second squared. And because we want just a length, wavelength, all right, we want meters to come out, we have to make sure that everything in the joule is wiped out. This is one of the times you have to use kilograms in chemistry. All right, most of the time we just use grams, but here definitely make sure you use kilograms. But anyway, the de Broglie wave equation, Planck's constant on the top, mass of the object in kilograms on the bottom, times the velocity, not frequency, the velocity that the particle is traveling, 1.3 times 10 to the 8th, and you get that very small 5.6 times 10 to the minus 12 meters. Now, in higher level physics courses, you'll see a version of this equation with some relativity thrown in. And if you've seen that, well done, that's pretty cool stuff. However, for Chem 221 through Chem 223, we won't be talking about relativity per se, so use the non-relativistic de Broglie wave equation. Ooh, there's something to impress your parents and friends with. But anyway, yeah, don't put the relativity part in here. Number 5, this is a series of questions where we're starting to talk about the quantum numbers. There are 4 quantum numbers. The first 3 are going to be the discussion of this problem, and the first 3 are n, l, and m sub l. So for this problem, we have an n equals 4, l equals 2, m sub l equals minus 1. And it says to what kind of orbital type does this refer? In the quantum number world, we're going to see lots of designations that look something like this. And we called it in the lecture the NL notation, and that's really what this question's all about. What is the NL notation for this set of quantum numbers? And it's not hard to figure out. The first number is the actual n number. The second letter, corresponds to a letter. And we talked about S, P, D, F, G corresponding to L of 0, 1, 2, 3, etc., etc. So for our problem, n equals 4. And if L equals 2, that means you have a D system. So you would write 4D for the answer here. The m sub L refers to one of the orbitals in the L subshell. L was like the subshell, like the type of house, and m sub L was the number of rooms or orbitals in there. And for the L equals 2 subshell, you have 5 possible m sub L values. So the L equals 2 house, there are 5 rooms. And m sub L of minus 1 is one of the 5 possible rooms in this house. Explain briefly why each of the following is not a possible set of quantum numbers for an electron in an atom. In each case, change the values to make this set valid. Okay, some of these are going to have more than one possible answer, by the way. This question introduces, as well as NL and M sub L, it also introduces MS, the spin quantum number, which is the 4th one. And the spin quantum number is helpful when you start putting electrons in the shells and orbitals around the atom. So for the first one, we got n equals 2, l equals 2, m sub l is 0, m sub s is plus 1. So n has to be a whole number, starting with 1, going up in theory to infinity, but you never have a negative n or a fraction, or a 0, something like that. So all of the n's here are okay. But l can be no bigger than n minus 1. As we saw in the last problem, l starts at 0 and goes up to n minus 1. So if n is 2, l could be no bigger than 1. So on the first one, there's definitely a problem with L, and we could change that to 0 or 1, and it would be okay. But the problem is with L. M sub L has to go from minus L to plus L. So if you changed it to L equals 1, then M sub L of 0 would be all right. You could also change the L to 0, and that would still be okay. M sub S will only be positive or negative 1/2. So hint, hint, what's going on in the next one. But anyway, B, n equals 2, good number. L can be no bigger than n minus 1, so 2 minus 1, 1. L of 1 is okay. If L is 1, M sub L has to go between negative L and positive L. So negative 1, 0, and plus 1 would be allowed values when L equals 1. M sub L of negative 1 is one of those, so M sub L is okay. But like we just talked about, M sub S can only be positive or negative 1/2. So M sub S is the trouble child here. You've got to change it to positive or negative 1/2, doesn't matter, and you're good to go. The last one, C. N is good. L goes from 0 up to 3 minus 1, 2. So L of 1 is okay. Absolutely. M sub L, negative L to positive L. So if L is 1, that means M sub L can be negative 1, 0, or plus 1. Plus 2 is certainly not in that range. So M sub L is the trouble child here. You could have negative 1, 0, and plus 1 for L equals 1. Those would all be fine answers, but you wouldn't want to have positive 2. That would be weird. And of course, M sub S on that one is okay too. What's the maximum number of orbitals that can be identified by each of the following sets of quantum numbers? Okay, number of orbitals is kind of a big deal. If you just have n, then n squared would be the number of orbitals. On the first one, though, you have an n and an l. And if you have something like that, and it's a legit combination, then 2l plus 1 would be the way to do it. So on A, if it was just n equals 4, then that would be something. But here we have n equals 4 and l equals 3. And l equals 3 is okay for n equals 4. If n equals 4, l goes from 0 up to 4 minus 1, 3. So that's okay. So if you just have the l value, then 2l plus 1 would be what you'd want to do to figure out the number of orbitals. So if l equals 3, that would be 2 times 3 plus 1, 7 orbitals total. So again, that was a good combination of n and l. None of the quantum numbers were broken. So 2l plus 1 would be the quick way. Those would correspond to all m sub l's from -3 to +3. So -3, -2, -1, 0, +1, +2, +3. Oh yeah. B, just got n equals 4, and that's a legit value of n. The quick way to do it, n squared. N squared would be 16. That's really awesome. Now, you could also figure out L values. L values go from 0 up to 4 minus 1, 3. And you could figure out the individual orbitals associated with L equals 0, L equals 1, L equals 2, L equals 3, etc. But on the other hand, why not just square it and stuff and be done with it? C, n equals 2 is a legit number, so no problem. But L equals 2. Now, if you remember, L can be no bigger than n minus 1. So if n is 2, the maximum L is going to be 1. So n equals 2, L equals 2 is not an allowed combination. And there are no orbitals that can handle n equals 2, L equals 2. That's a bad combination of quantum numbers. So you would say no orbitals would work for that one. And then finally, the last one, n equals 3 is okay. L of 1 is certainly under 3 minus 1, 2, so that's okay. M sub L needs to go from -1 to +1, so all three quantum numbers are okay. If you have all three quantum numbers as being okay with each other, then that just corresponds to one orbital, all right? And let's look at that one a little bit more. So if you had n equals 3, it would be 3 squared, 9 orbitals, but we have L equals 1, so that's like a subset. So if L equals 1, 2 times 1 plus 1, 3 orbitals would correspond to L equals 1, and the values of M sub L would be -1, 0, and +1. But then it's saying specifically, we just want the M sub L equals -1 orbital. That's going to be just one orbital in that set. State which of the following are incorrect designations for orbitals according to quantum theory. 3p, 4s, 2f, and 1p. Briefly explain your answer. Okay, there's a couple different ways to do this one. One way is to literally read a periodic table. And like we talked about, you can read like which regions you're in. So like the S block is groups 1a and 2a with helium thrown in. And the P block is 3a through 8a, or boron through neon, and basically down. And you can find the period number to correspond with S and P. The F blocks are the lanthanides and actinides, and the P's, like I said, are on the right side. Now, as you fill in the electrons, if you remember, it's like 1s electrons first, 2s electrons next, 2p after that, but there was no 1p. So if you know about electron configurations, there are no 1p electrons, all right? It doesn't work. And so reading the periodic table, you'll see that there are no 2f's and there are no 1p's. The first F block is 4f, the first P block is 2p, but there is a 3p block, that's aluminum through argon, and there is a 4s block, that's potassium and calcium. So reading the periodic table is one way to do this. A possibly easier way, though, is to use an Aufbau diagram. And here's the one that we used in lecture I talked about, but you can use any one you want. And if you look at this diagram a little closer, you'll see that the first p orbital is the 2p. Like 1p would be right there, but it's not present, all right? If it's not on the Aufbau diagram, then it's an incorrect designation for an orbital. And you can see up here, the first F is a 4f, so 2f would be like right there, and that's not going to happen either. So you can use an Aufbau diagram, and again, you can build this yourself or use the one in the table, either way, and that's fantastic. You can also read the periodic table to see what's happening too. For this question, we're being asked how many nodal surfaces, planar and spherical, are associated with each of the following atomic orbitals, 4f, 2p, and 6s. Okay, planar nodes equal the value of L. And in the lower right-hand corner there's the L values with the corresponding letters. And spherical nodes equal n minus L minus 1. So for this problem, we want to find both the n and the L value and then just plug it in. So for example, on A, the F, if you look in that little table, means L equals 3, and the number 4 there, that is the n value. So for 4F, you're going to have 3 planar nodes because L equals 3, and if you figure out the spherical nodes, 4 minus 3 minus 1, 0 spherical nodes. So again, figure out n and L. You can see we're going to use this a lot, and then you can find the nodes from there. For 2p, we have n equals 2, and p means L equals 1, so that means 1 planar node, and 2 minus 1, 0 spherical nodes. On 6s, n equals 6, and s means L equals 0. So there aren't going to be any planar nodes because L equals 0, but we're going to have 6 minus 0 minus 1, 5 spherical nodes for the 6s. So it's pretty easy to figure out how these things work, but you do need to know how to find n and L from the little designation. It's not too hard. You've totally got this. Cool. Write the electron configuration for magnesium and argon using both the SPDF, which is also known as spectroscopic notation, and orbital box diagrams. All right, so first you have to know how many electrons that are in both of these atoms. So again, the periodic table will be very helpful. Magnesium is number 12, so that means 12 protons, but a neutral atom of magnesium will also have 12 electrons. And likewise for argon, argon's number 18, so neutral argon will have 18 electrons. You always start with 1s, and you work your way then to 2s, 2p, 3s, 3p, 4s, 3d, etc., according to the Aufbau diagram. So if you're new to this, I highly recommend that you follow the arrows on the Aufbau diagram. We will always start with 1s, all right, and then we'll move to 2s. The other thing is that s's always hold 2 electrons. P's, regardless of the number in front of them, will always hold 6, D's will hold 10, etc., etc. So magnesium would be a 1s2, 2s2, 2p6, 3s2 electron configuration. And that's the SPDF notation or spectroscopic notation. If you wanted to call this neon in brackets, 3s2, you could. That's totally fine. The noble gas notation is awesome. Now, the right-hand side shows the orbital box notation. And orbital box notation is great for seeing if something is paramagnetic or diamagnetic. Each orbital is represented by a box. So the s orbitals have 1 box. The p's will have 3. Remember, p means L equals 1, m sub L negative 1, 0 plus 1. You are literally seeing the 3 m sub L values, negative 1, 0, and plus 1. D's would have 5 because negative 2 to positive 2, etc. But anyway, same thing, just plug them on in. 1s2, 2s2, 2p6, 3s2, you're good to go. Magnesium has just as many up electrons as down, so it's considered diamagnetic, which we'll talk about later. Argon, very similar. It has everything that magnesium does plus 6 more electrons, and the next one is a 3p system. So that would be a 3p6, 1s2, 2s2, 2p6, 3s2, 3p6. There's the orbital box notation. Again, every up has a down, so this is again a diamagnetic atom. In the second part of this problem, I would like you to use SPDF and noble gas notation to write the electron configurations for these two elements. And the first is strontium. Strontium's number 38 on the periodic table. Apparently strontium is named after a town in Scotland. Well, anyway, 38 is the total number of electrons in a neutral atom as well. So if you're going to write out the electron configuration, you'd go up to krypton, number 36, and then use the electrons past that. On the other hand, you could start directly with krypton and go from there. So if you do this, the complete electron configuration, 1s2, 2s2, 2p6, that gets you to neon. 3s2, 3p6 gets you to argon. 4s2, 3d10, don't forget the 3d's in there. 4p6, that gets you to krypton. 5s2. But the noble gas notation version, which is of course a lot easier to write, would be krypton in square brackets, must use square brackets, krypton 5s2. So krypton includes all of that up to 4p6, and then you can put 5s2 after it. Don't forget the 3ds. 3ds, 4ds, 5ds, as well as later on 4fs and 5fs will sneak in there sometime. So just kind of realize that they can be important. Now tin, which is number 50, is just a little bit to the right of strontium. So you'll have all the electrons of strontium, which includes up to 5s2, but then you'll have 4d10, 5p2. All right, so a little bit different. So the noble gas version of tin then would be krypton, again in square brackets, 4d10, 5s2, 5p2. Now notice in that noble gas notation, I put 5s2 after the 4ds. This is what they call increasing n notation. So you can see that 4d as an n of 4, 4d10 is listed before the 5s2, and 5p2 electrons. And there's a reason for that. It has to do with taking away electrons, and we'll talk about this in a little bit. So you can write the noble gas notation for tin as krypton 4d10 5s2 5p2, which is what I did, or you can also write it krypton 5s2 4d10 5p2. That's the electron filling order, and honestly either way is fine, but I bring this up because you will see both methods listed. I'll talk to you later about why kind of it's cool to have the 5s and 5p electrons after the 4d. It has to do with making the ions of tin, which is something we'll talk about in a little bit. Anyway, either way is great. In this question, we want you to write the orbital box diagrams for the electron configuration of these ions. Now, an ion is just an atom with one or more electrons that have been lost or have been gained. So you can see the first two are cations. Na+ has lost an electron. In the second one, aluminum 3+, aluminum has lost 3 electrons. But the third one is an anion, a negative ion. So in this case, fluorine has gained an electron to make the F-1 ion, or the F-1 anion. No big deal. How I work on these usually is I start by writing the neutral version of the atom first. So as an example of this, sodium is Na, which is number 11, has an electron configuration 1s2, 2s2, 2p6, 3s1. So that's neutral sodium with all of its electrons. And if you count up those superscripts, that equals 11, which is 11 is the atomic number of sodium, which is equal to the number of electrons in a neutral atom, etc., etc. However, in this problem, we want to figure out the sodium plus cation, i.e., what's the electron configuration of sodium without one electron. And what you want to do when you're taking away electrons is you always take away electrons from the highest n. Now, the numbers that are in front here, the 3, for example, in 3s, as well as the 2s in front of the 2s and 2p's, and the 1 in front of the 1s, those are the n values. And highest n comes out first, followed by highest n plus L. So in this case, highest n is 3, the 3s electron. That 3s1 electron is going to be the first electron out. So sodium with a +1 charge is going to have 1s2, 2s2, 2p6. Now, in orbital box notation, 1s2, you'd write one box, like right there, with one up arrow and one down arrow. And you can see how the 2s is the same thing, one up arrow, one down arrow. The p's, however, there are 3 orbitals, so we write 3 different boxes. So the 1, 2, 3 electrons would go in first, like spin up, and then 4, 5, 6 would be the electron spin down. That's going to give you the 2p6 part right there. So in SPDF notation, it would be 1s2, 2s2, 2p6, but because this one was referring to orbital box notation, this would be a better way to show it right there, which is totally fine. For aluminum, neutral aluminum has 13 electrons. So that would have a 1s2, 2s2, 2p6, that gets you to neon, 3s2, 3p1 configuration. This would again be SPDF, not orbital box notation. But again, we're going to take away some electrons here because it's aluminum 3+. We're going to take away 3 electrons. Now, in this molecule, notice again the N values. We have 2 things which have a 3 in front of them. So the official rule is you take away electrons from highest N first, and if there's a tie, highest N plus L. Punchline, what that means is that if you have a tie, the last ones in are the first ones out. So highest N plus L between 3s and 3p would be 3p. So what that means is that first electron is going to come out of 3p1. We're going to take that one away first, but we have to take away a total of 3 electrons. We need to take away 2 more. That means those 2 are going to go away. Aluminum 3+ is also going to have 1s2, 2s2, 2p6 configuration. And if you write out the orbital box, this is what it looks like. Now notice that both of these ions have the neon electron configuration happening, all right? And sometimes I'll say how the noble gases are like the cool kids in the back of the bus. All the ions want to be like them. They will literally lose or gain electrons usually to become like a noble gas. And that's what both sodium plus and aluminum 3+ here have done. They are both looking now like neon, if you will. They have different number of protons, but their electrons look just like neon. And this is a trend that we see a lot of times in chemistry. Now, the last one there is fluorine. Now, neutral fluorine is 1s2, 2s2, 2p5. And like you've seen here on the sodium and the aluminum ions, when you're writing the 2p, you have 3 boxes. And if you have 5 electrons, the 2p5 to put in, let me use a different color here, there would be 1 electron, 2 electrons, 3 electrons, and then you start pairing up. This is Hund's rule because you don't want to have 2 electrons in the same box unless you have to. So the 4th electron would be spin down right there, and the 5th electron would be spin down on that one. But there's like 1 space available, all right? That final 2p box only has 1 electron inside it. Well, fluoride, which is the fluorine ion with a -1 charge, has 1 extra electron. And you can probably figure out this extra electron is going to go in the lowest unoccupied spot. So there I've written that electron arrow in green, if you will, to show that it's going to go in that 1 empty spot in fluorine. So fluoride, fluorine with a -1 charge, 1s2, 2s2, 2p6, guess what? Just like neon, it's going to be one of the cool kids in the back of the bus as well. It's got the same electron configuration. So in this problem, I hope you can see then that when you're taking away electrons, highest N first, so the 3 electrons came out before the 2s and the 1s, highest N first, and if there's a tie, then highest N plus L, which means last one's in, first one's out. On the other hand, when you're making an anion, you want to add electrons to the lowest unoccupied spot available. So fluorine had a 2p5. We added 1 electron to make the F-1 ion. That extra electron went into the 2p5 to make it 2p6, and all of them have a neon core. Arrange the following elements in order of increasing size. Okay, so some of these are about the different periodic trends. And remember, if you see anything that has to do with size, and that'll be definitely this one, A. It's also going to be D down here. But anyway, when it comes to size, you want the atom which is most left and down. And that would be the one that you would predict would be the largest. All right. So if you look at those elements on there, the element which is most left and down of all of those is rubidium. So if you're going to put these in order of increasing size, you start with the most upper right and move to the most lower left. All right. So phosphorus to germanium to calcium to strontium to rubidium, that would be the order you'd want to go. And like I said in lecture, I'm not going to ask you questions about these kind of things between like boron and silicon, B and Si. One is more left and one is more down. Which one? That would be a bad question. If you have to guess in the real world, usually the lower one is bigger than the left one, but that's kind of weird. Now, B and C are about ionization energy and electron affinity, and those two trends increase up and to the right. So the answer on both B and C is going to be the element which is most up and to the right. So for the first one on B, O, S, and Se, they're all in the same column. The highest one is oxygen. So oxygen should have the largest first ionization energy. And the same thing on C, you want the one which is most up and to the right. And of those three elements, chlorine is most up and to the right. Now, for largest radius on D, all right, there's a couple things going on here. But notice how we have two anions, two negative ions, and a neutral atom. Anions are always bigger than the neutral atoms they come from. Cations are always smaller than the neutral atoms they come from. But in this case, then, if you're just comparing oxide and fluoride, the left and down thing works really well. So for D, oxide is certainly the biggest. It has the fewest number of protons and the greatest number of electrons. So that means the kids can go crazy relative to the parents, which is what I talked about in lecture. Just realize the 8 protons aren't able to hold on to those 10 electrons as well as they are in fluoride, where you have 9 protons and 10 electrons, or in fluorine with 9 protons and 9 electrons. And then finally, this last one, which is the most paramagnetic, iron 3+ or chromium 3+. What I would do on these is, first of all, figure out how many electrons are left over for the atom. So, for example, for chromium is number 24 on the periodic table. So chromium would have an argon 4s2 3d, I think 4, yes, a core, all right. And if you're going to make positive 3, well, you have to remove the 4s electrons first. So on chromium plus 3, because N if 4s is bigger than N equals 3, the 4s come out first. And iron plus 3 would have 1 less, or 3 3d electrons. And if you draw out cheesy orbital boxes, which is what I've just done, there's 5 orbital boxes for 3Ds, each electron in its own orbital, that's Hund's rule, chromium plus 3 would have 3 unpaired electrons. Now, if you do the same thing for iron, iron is an argon 4s2, and I think it's 3d, 1, 2, 3, 4, 5, yes, 3d6, good. And again, like last time, if you're making iron plus 3, the first electrons out are the 4s. All right, that's a weird thing about transition metals. The s's usually come out there before the d's. And then you'd have 3d5. So 1, 2, 3, 4, 5. Those are the 5 3d orbitals. If you have 5 electrons, they each go in their own room. Again, this is Hund's rule. So iron plus 3 would have 5 unpaired electrons. Chromium plus 3 only 3. We would say that iron plus 3 is more paramagnetic. More unpaired electrons for us right now means more paramagnetic, and iron plus 3 certainly has more unpaired electrons than chromium 3. Punchline on E is to remember that if you're making an ion, a positive ion from a transition metal, take the 4s or 5s, whatever, electrons out first before you start touching the Ds. Higher N comes out before other ones. Cool. Naming compounds is very important in chemistry, and being able to name them and talk to each other about which chemical we're using is really important. So this question is just going to ask you about most likely charges and formulas for these different species. So as an example of this, then, the first one is the selenide ion. Now, selenide comes from selenium, and if you look on the periodic table, selenium's number 34. What's important here is that the selenide ion, IDE, means it's going to be negative. So if you look at selenium on the periodic table, it's in group 6A. And group 6A, all of those nonmetals, they want to be like noble gases. So they're going to gain 2 electrons to go to the nearest noble gas, which in this case would be krypton. So selenium, when it becomes selenide, is going to gain 2 electrons. It's going to be Se minus 2 or Se2 minus. All of the group 6A nonmetals, group number minus 8 is how you figure out their charge. All of them, 6 minus 8, minus 2. So oxygen as oxide, minus 2. Sulfur as sulfide, minus 2. Selenide, minus 2. Telluride below it, minus 2. They're all going to be minus 2. So all of the nonmetals, it's group number minus 8 to figure out their negative charge. Potassium represents a fixed charge metal. There's only some of these, but groups 1A, groups 2A, and the stairs on the periodic table, those are all fixed charge metals. So potassium is number 19, but if you look up at the top, it's in group 1A. Potassium will always be a positive 1 charge. So that means sodium above it, lithium above that, as well as rubidium below potassium and cesium, all those things, positive 1 charges. All right, all the group 1A metals have positive 1s. And group 2A would be positive 2. So for example, magnesium would be positive 2 and calcium would be positive 2, et cetera, et cetera. Now, the next one you can see there, I put trick. So I'm trying to make you think here a little bit, basically. And I wanted you to figure out the charge on an iron. Well, iron is not a fixed charge metal. It's not in groups 1A, groups 2A, or the stairs. It's a transition metal. It's number 26 on the periodic table. This means it's a variable charge metal. So what this means is that if someone even asked me with my PhD, what's the charge on an iron? I would say I don't know, because iron is all over the spectrum. Iron can be as low as positive 1 and it can be as high as positive 8. So iron is all over the place. So if you put I don't know for C, that's fine. The most common charges on iron are positive 2 and positive 3. And this might be what some of you put down, which is fine. However, just realize that's not necessarily what the charge on the iron's going to be. Variable charge metal means we don't know, and we need some way to communicate with each other as to what the charges will actually be. So iron, it is okay to say, I don't know. All right. If we had an iron positive 2 ion, we would say iron Roman numeral 2. And if we had iron plus 3, we'd say iron Roman numeral 3, those kind of things. That's the way that scientists get it across to each other as to which iron they're using. But to just tell you what the iron charge is, no way. Who knows? Hard to say. The next several examples are polyatomic ions. And polyatomic ions are just very common combinations of ions that stick together and have a charge. Permanganate is kind of a cool purple color when you see it in solution. Permanganate is MnO4 with a -1 charge. So that's a manganese, 4 oxygens, and they all stick together, and they overall have a -1 charge. And it's a very, very common polyatomic ion. So you kind of just need to know / memorize this. I recommend using flashcards, or you can use a Quizlet or something like that, but make sure you start learning these because we're going to run into them all the time. Nitrite is another polyatomic ion. Nitrite is supposedly the bad ingredient in hot dogs and a lot of the heavily processed meats. Nitrite is NO2 with a -1 charge. So this has a nitrogen, 2 oxygens, and those 3 atoms together have a -1 charge. And we do run into it quite often in chemistry. Phosphates we run into a lot as well. Phosphate is, again, another polyatomic ion. Phosphate is PO4 with a -3 charge. Now notice that the last one had an ITE and this one has an ATE ending. Ions, polyatomic ions with ITEs and ATEs will always have oxygen on them. So that's one way to tell you've got something with oxygen anyway. You're going to have oxygen because of the ITE and the ATE ending. If you look at the very bottom down there, sulfite is going to be one of them we'll look at. That's got an IT ending. That's going to have oxygen. So that's kind of cool. Now, the G, though, the next one that we're actually supposed to talk about is the dihydrogen phosphate ion. Now, hydrogen, most of the time with these problems, will be H+. And you can see there's a Greek prefix of 2, di. So that means we're going to have 2 H pluses joining with the phosphate. So what's going to happen then is when we make this dihydrogen phosphate, it's going to be H2PO4. We're literally just combining those atoms together. And the -3 of phosphate will be added to 2 positive ones of hydrogen. So -3 plus 2, this thing is going to have a -1 charge. So dihydrogen phosphate, H2PO4 minus. If you see hydrogen phosphate ion, that's HPO4 minus 2. It's in between those two species. It's not a -3 phosphate. It's not a -1 dihydrogen phosphate. Hydrogen phosphate would be HPO4 minus 2. Ammonia is one of the few positive cation polyatomic ions. So it's a polyatomic ion with a positive charge. Ammonia is NH4 plus. And ammonium is different from ammonia. Ammonia is NH3. And if NH3 gets an H plus to it, it becomes ammonium. So NH3 is ammonia, NH4 plus ammonium. And then finally, sulfite there. Sulfite is sulfur. It's got some oxygens on it. Sulfite is SO3 minus 2. Now, sulfite is a lot different than sulfur trioxide. That would be SO3 without a charge, a neutral compound. Sulfur trioxide, the gas, is actually a precursor to sulfuric acid. If you put sulfur trioxide in water, it actually makes H2SO4, sulfuric acid. That's not good. On the other hand, sulfites are actually relatively benign. Sulfites can be a preservative in wines. And if you have a allergy to sulfites, you may want to avoid wines with sulfites in them. But anyway, sulfites are relatively safe to drink, especially compared to sulfur trioxide in water, which would make sulfuric acid. So there's a big difference, punchline, between sulfite, SO3 minus 2, and sulfur trioxide, which is SO3 without a charge. In this question, we want to give the name from the formula or the formula from the name. And so in this problem, what we'll do a lot is we'll look at what kind of compound it is. Is it a variable charge metal? Is it a fixed charge metal? Or are they nonmetals plus nonmetals? So on the first one there in the upper left corner, KBr, potassium is a fixed charge metal, and bromide, Br, is a fixed charge nonmetal. So when K and Br come together, they will only come together as KBr, because K is always +1 and Br is always -1. You will never have a K2Br or a KBr2, something like that. It's always going to be KBr. So if you see a fixed charge metal with a nonmetal, it's literally the name of the metal plus the nonmetal with an IDE ending. So this would be potassium bromide. All right. And that's pretty cool. The next ones, however, the next two examples have copper. And copper is an example of a variable charge metal. So what that means is we don't always know what the charge on the copper is going to be. If you have a variable charge metal, you need to include a Roman numeral next to the variable charge metal's name. And to figure out what the charge is, we use the nonmetals. So chloride, Cl, is always -1. 1. It's group 7. 7 minus 8 is minus 1. And there's 2 minus 1 chlorides. So that's going to be a positive 2 copper. So we would write this next one as copper 2 chloride. Copper 2 comes from the fact that it's a positive 2 copper, and chloride is negative 1. Now, a hint that sometimes helps with these is something called crossover. Crossover does not work 100% of the time. I want you to know that right now. But it does work more than 90% of the time, which means it can be kind of helpful, especially when you're learning. The 2 of the chlorine, you can put it on the copper, and there's like an invisible 1 by the copper. There's 1 copper atom. You can put that by the Cl. So what this tells you with crossover, that 1 is the charge on the chloride, and chloride, sure enough, is minus 1. And the 2 by the Cl, that's going to be the charge on the copper, copper plus 2. And sure enough, crossover works really great here. This is a copper 2 chloride species. So if you're having troubles finding the charge on the variable charge metal, crossover can be a nice way to figure this out. The next one has copper with 2 nitrate ions. Nitrate is a polyatomic. If there's more than 1 polyatomic ion, you use parentheses, but that's the only time you use parentheses, only if there's more than 1 polyatomic ion. Now, if you cross it over, the 2 on the nitrate will be the charge on the copper, and the 1 copper atom, the 1 will be the charge on the nitrate. And sure enough, nitrate is minus 1. There's 2 of them, so that means that negative 2 nitrates has to be balanced by copper. It's going to be a positive 2 copper. So this compound is copper 2 nitrate. And crossover works really, really well here. No problem, just cross them over. However, crossover does not always work. And the next example is one where crossover does not work. So notice that if this was a crossover compound and you wanted to figure out the charge on the titanium, you'd say, well, there's a 2. That's going to be the charge on the titanium. And there's 1 titanium, so that's going to be the charge on the sulfate. You might say then that this would be a titanium 2 sulfate. But that does not work here. So let me erase all that. And why it doesn't work is because sulfate is a minus 2 polyatomic ion. It does not have a minus 1, which is what crossover would predict. And minus 2 sulfate times 2 sulfates is a total of minus 4. That means this titanium is going to have a positive 4 charge. So this compound here is titanium 4 sulfate. Roman numeral 4 is IV. This is why it's so important to know your polyatomic ions and their charges, because it'll help you then, in case crossover breaks down, it'll help you to see what the actual name will be, which is kind of important. The next 2 examples are nonmetals with nonmetals. Nonmetals are everything up and to the right of the metalloid line, so nitrogen and oxygen definitely follow in that category. And how you name these, the first name of the element is just given, and the second name, you add an IDE ending to it. The second atom, you always add a Greek prefix to it, but you only add a Greek prefix to the first atom if there's more than 1. So NO2 would be nitrogen dioxide. There's 1 nitrogen, we just call it nitrogen, and then 2 oxygens would be di, and the second one gets an IDE ending, nitrogen dioxide. The next one is similar. However, notice that there's more than 1 nitrogen, more than one of the first atoms listed. So if there's more than one of the first atom listed, definitely put a Greek prefix in front of it. So that'll be a di-nitrogen. But you also always put a Greek prefix in front of the second one. So even though there's only 1 oxygen on the next example, we're going to still put mono in front of it, and we're also going to change it to oxide because it's the second one listed. So putting this all together, di-nitrogen monoxide or monooxide, either way is fine. So this is the kind of the punchline here. More than one of the first one, add a Greek prefix, but if only 1, don't add a Greek prefix. The second atom listed, you always put a Greek prefix and always put IDE ending. Good to go. On the right-hand column now, we're going to do the same thing. We're going to find the formula from the name. Now, aluminum is one of the stairs elements. Aluminum is a positive 3. This is one of the things you have to know / memorize. It's aluminum, gallium, and indium. Those are all positive 3. Zinc and cadmium are positive 2, and silver is positive 1. Iodide comes from iodine on the periodic table, and iodine is a group 7A nonmetal. 7 minus 8, iodide's going to have a -1 charge. Now, when you're making a formula, it has to be neutral, so you have to make sure all the positives and negatives cancel out. If we had just one aluminum for every one iodide, you'd have positive 3 and -1. You'd still have a positive 2 charge left over. So we will add 3 -1 iodides. -3 from the 3 iodides will cancel the positive 3 of the aluminum. Ali3 would be the formula. Neutrality is always the name of the game when you're making a formula. The next one is a cobalt, and you see there's a Roman number 2, and that tells you then that you have a cobalt with a positive 2 charge. And this is really cool because cobalt is a variable charge metal. Even I don't know what cobalt is, all right? You just don't know. There's lots of different variations of cobalt, and it really is cool to have the Roman numeral there. Now, oxide comes from oxygen. Oxide is -2. So if you put a positive 2 and a -2 together, those charges will cancel out. Cobalt to oxide will be just COO. And again, make sure that you have a lowercase o for cobalt there, but a capital O for the oxygen as oxide. Good to go. Next one, chromium 3 means you have a chromium with a +3 charge. Now, here's where it gets kind of tricky. IDE is usually for the elements as -1s. And it might be tempting at first to think of the next one as chlorate, as chloride, all right? But it's not. It's an ATE. And like we talked about earlier, the ATEs will a lot of times have oxygens to them, and chlorate is no exception. Chlorate is a polyatomic ion. It's ClO3 with a -1 charge. So that whole ClO3 thing there has a 1- charge on it. Well, we need to balance it out. We need to make a neutral compound. We're going to need 3 chlorates for every chromium +3. So we would write this Cr parentheses ClO3 parentheses 3. That's chromium 3 chlorate. Next one, uranium 4 would be uranium with a +4 charge. Sulfate, SO4 -2. You're going to need 2 -2 sulfates to balance that +4 uranium. U parentheses SO4 parentheses 2 would be uranium 4 sulfate. The next one, phosphorus and iodide. Phosphorus P and iodide I are both nonmetals. So this is literally going to be nonmetal plus nonmetals. That's why we're seeing Greek prefixes, tris, and the next one's monos. Notice there have been no Greek prefixes with anything with a metal, and that's really important. That helps the chemist to figure out what kind of compound you have. But anyway, tri is 3. Phosphorus means 1 phosphorus. Triiodide means 3 iodines. Pi3. And the next one's probably the most famous of all these compounds. Dihydrogen monoxide would be 2 hydrogens and 1 oxygen. The oxygen is listed last. H2O. This is the formal name for water. Now, of course, everybody calls dihydrogen monoxide water, all right, because it's, less syllables and all that jazz. However, the official name of water is dihydrogen monoxide. You are now hip to some of the rules that happen in chemistry. Oh, joy. Here's another problem where we're going to find the name from the formulas, and we're going to call these by their acid names, by the way, if it becomes relevant. Okay, so HCl as an acid, by the way, is an acid because H is listed first. If H is listed first in a compound, that tells you it's an acid. So this is hydrochloric acid, all right? No oxygens, so that means hydro. It's chlor because of the chlorine. Hydrochloric acid is HCl, and it's a very common acid that we'll use in lab and stuff like that. The next one is also an acid. The H is listed first. Nitrate is NO3 minus 1. Nitrate as an acid becomes nitric acid. Nitric acid is also a very common acid. It has some different properties from hydrochloric acid, as we'll see. So HNO3 is nitric acid, HCl hydrochloric acid. NaOH is a metal with a hydroxide. Hydroxide is OH minus. And if you see a metal like sodium with a hydroxide, that means that it's a base. Bases are kind of the counterpart to acids. We'll talk more about this in a future lecture, but I just want you to start hearing the term base because it'll be important to us. But to name them, they're pretty chill. Sodium is a main group metal, so we don't need Roman numerals or anything like that. It's just sodium, and it's with hydroxide, sodium hydroxide. If you've used Drano at your house before for perhaps a drain which is clogged, sodium hydroxide is the active ingredient in Drano. It's very powerful stuff. The next one is an example of a hydrate, and hydrates are not something we'll see a lot of, but I do want you to hear these terms in case you hear them. First of all, let's look at the COI2. Cobalt is CO, and that's a variable charge metal, so we'll need to put a Roman numeral next to that. Cobalt is in the middle of the transition metals. It's not groups 1A, groups 2A, or the stairs, so that's why we're going to need a Roman numeral. Iodide is always -1, and there's two of them, so that means the cobalt is going to balance that -2 with its own +2, so that's a cobalt +2. COI2 will be cobalt 2 iodide. This compound has two waters after it. If you see a .2H2O or .5H2O or something like that, it's always Greek prefix hydrate. So in this case, that would be a di, because 2 is di, and then the water means hydrate. So we'll call this one cobalt 2 iodide for the cobalt 2 with the 2 iodide -1s, and then dihydrate. So cobalt 2 iodide dihydrate is the fancy name for that compound. The next column, HBr. Notice how HCl was hydrochloric acid. Chlorine became chloric acid. HBr is the same thing, except now we have bromine, so that's brome instead of chloric. HBr, hydrobromic acid. All right. ClO4 is the perchlorate ion. The H is listed first, so this is an acid. So in this case, HClO4 becomes perchloric acid. Perchloric acid is a real powerful acid. Lots of really interesting things you can do with it. But for right now, just know that H is listed first, so it's an acid, and the perchlorate ion becomes perchloric acid when added to an H+. KOH is similar to NaOH, which we saw. NaOH was sodium hydroxide. Well, K, as you probably know, is potassium, so this will be potassium hydroxide. No problem. And then NH3 is just something we'll run into often in this class. NH3 is ammonia. Now, you could call this nitrogen trihydride, but hardly anybody does that. Almost everybody calls it ammonia. And remember, ammonia, NH3, is different from ammonium, NH4+, the polyatomic cation. Oh, joy. Okay, so that's it for problem set number 3 of Chemistry 221. You're good to go. If you have questions on any of this material, there's lots of resources to help you kind of make sure it's all good to go. There are study guides and concept guides in both the companion and online. There's also the online-only chapter guides, which have lots of resources to help you. And of course, if you have questions, you can reach out to the LSC/Avid Center located above the library, and you can definitely let me know too. I am happy to help. All right. Thank you for spending your time with me. I hope this has been helpful. Have a wonderful day.